In this video, I'm illustrating how to find the refractive index of the medium, the different materials, maybe water or glass. Okay, so first of all, I will talk about what is the refractive index, and then I will show you how to measure refractive index of different materials by simulation, that is virtual lab. Okay, so first of all, you may have seen some physical phenomenon like this. If you have a water like this and you put something here, for example, a pencil, right? You can see some kinds of bending like this at the interface, right? You can see like this pencil is broken right here. Why? You can observe this phenomenon. Why pencil looks like broken at the interface of right here is air and this is water, right? So this phenomenon of light is said to be refraction of light. That means when light passes from one medium to the another medium, right here, here is air, right? And then this medium is water. What is the difference between these two? The difference is water is denser than air, right? One medium is rarer and the other is denser. There is the difference in density. So what happens is when light passes from one medium to another medium, the velocity of light changes. Because of that, uh, the velocity of light decreases in general when it passes from vacuum or air to the some medium like air, not air, like glass or water or something else. Okay, like diamond. So, how to find the refractive index? So we know the definition of refraction, right? It is the phenomenon in which light bends when it passes from vacuum to the medium. Okay, so velocity of light is maximum in vacuum, and in the medium, velocity will be decreased. Okay, so let's go back. I will show you the Snell's law, which is very helpful law to find the refractive indices of different mediums. It's right here. Okay. In general, our definition of refractive index symbol is n, or sometimes it is denoted by mu, which is the Greek letter, and it is called mu. And it is symbol for refractive index of the medium. Okay, and in general you can symbolize by n also. These are two common symbols to represent refractive indices. Okay, so right here is the Snell's law. What is n1? N1 is the refractive index of first medium. You can say any medium. Here might be water, and right here might be like the diamond or glass or something, right? For this case right now, here is air. So refractive index of this medium is N1. Okay, and the refractive index of this medium, this may be glass slab, or it could be like water or diamond, whatever. Okay, but this medium is different than this one. That's why refractive indices is different, are different, right? Here is N1 and here is N2. Okay, so in general, our definition is velocity of light in vacuum, which is denoted by c, and velocity in medium. This is the definition of refractive index n is equal to c divided by b. Remember here, velocity of light in vacuum is maximum, which is 3 into 10 to the power 8 meter, right? You know this from the previous lectures. we did it in several classes. We know, but this is the maximum possible velocity, that is velocity of light in a vacuum. Okay, so velocity of light in medium is always less than that. That means something like 2.9 into 10 to the power 8 meter per second or something. Okay, so 10 to the power 8 power is, okay. So if you divide by a smaller number to a bigger number, your value will always be greater than 1. So refractive index of the medium could not be less than 1, right? Because this is the maximum value, and wherever light goes other than vacuum, the velocity will decrease. If numerator is 3, and if you divide by something less than 3, the quotient will be always more than 1, right? So this is the one thing you need to know. Okay, right now in this experiment, we have to deal with the Snell's law. So Snell discovered a very useful law, which is right here. Let me go back, grab a pencil and circle this law. So this law gives you the relationship between angles that we call angle of incident right here. This one, which is the incidental light rays making angle with normal. This is imaginary normal. You can draw a perpendicular line in the surface at which incident ray is contacting, right? So if you measure this angle, we can call theta 1. So n1 is refractive index of this medium, say air, n1, and theta 1 is angle made by incident incident ray with normal, right? This is theta 1. So what is N2? N2 is refractive index of this medium. Say this is glass slab. This is glass. Okay. It could be water also. It could be diamond also, whatever. But say this is the glass slab and its refractive index is N2. Okay. So this angle right here we call the refracted angle, right? So this is the refracted ray. Refracted means it is bending, right? If this glass slab is not here, the path of this ray should be straight like this, right? It will follow the same path from here, but it is bending by some degree right here. Okay, so our goal is uh, to measure this angle and this angle. This is theta 1 and this is theta 1. This is incident angle, put it here, and this is refracted angle. Okay, so Snell found the law, the relationship between refractive indices of the medium and angle of incident, this theta 1, and angle of refracted theta 2. Okay, he put in this format, which is n1 sine theta 1 equal to n2 sine theta 2. Okay, so this is the law. So from this one, if you don't know, it is easier to measure the angles. You just need a protractor to measure the angles. This is the simple variable. So if you don't know in a refractive index of one of the medium, suppose you don't know n2, but you know n1, right? In general, refractive index of air is 1, right? So if you don't know n2, what the refractive index of the other medium like glass or water, then you can do this experiment, right? So for example, the refractive index n1 for air is 1. So you measure this theta 1 and you put it here, sine theta 1. Suppose you get 60, right? You can write like this, 1 into sine 30, right? And I will show you later in actual simulation data, right, equal to, you don't know N2, that you need to find out. And when you measure this angle theta 2, you may get something like sine 25 degree, right? So you have everything. This is the constant value you will get once you insert into calculator, and then you will get certain value from here also. Easily you can find the N2. Okay, so the main objective of this lab is to uh, calculate refractive index of some medium. Okay, so let me go to the uh, actual lab. I believe you understand the physics of refraction of light. And let me go to here, procedure to find refractive index. You can read all these instructions. I will show you according to all these instructions. If you click it here in this link, you will lead to this window. Okay, right here uh, you have two boxes on the right. Here is the material. You can choose any material, but we need air. Above right here, we have air, right? Medium is air. So I can put it back in this box. It was not there. Initially, I can turn off this light laser, and then here is the mystery material. So I just need, according to the manual, you have to set glass, right? This is your first goal. So you can see here the refractive index of refraction, which we can call N1, right? It is 1. This is for air. If you choose different material, this value will come something different. Okay, this is air. If you just put water right here, see here, water is this much. If you put somewhere between, it will come something else, right? If you put glass is 1.5, and if you go ahead, it will be this much. Okay, just put air, and then this one is glass, which is 1.5. Okay, so uh, what are the things you need to do? Yeah, just do like the setting things. This is the normal line. Okay, you have to put the norm. So you can move this one up and down, up and down. So you can hold it and move up and down. Okay, so you can see in wave format if you want. Actually, light is a wave, right? It behaves like this, but we don't need to see wave because we can't measure exact angles of incident and refraction. So I wanted to keep this one, right? Okay. So after setting all these things, your goal is to see, first you have to observe by putting air as a material for first medium and glass for second material, right? So now uh, you can measure the angle of incident and angle of refraction. Okay, so I think first thing is you just have to see the Snell's law, whether it is verifying or not. To do that, what you can do is uh, here is the protractor. I wanted to see whether it is okay. So here is 0, right here. So I just have to align this 0 line with this vertical line, which is normal, so that I can measure angle, right? And then this horizontal line also should measure here. It's almost correct. You should be very careful while doing a lab. This is experiment, and if you are careless or something is wrong, then we can't get the right value. Okay, so uh, so first thing is just to check it. You don't have to take whole data and find there is no table for this first part, right? Just air and the first medium air and second medium glass. You just have to check it. Check it means, for example, I can put this angle of incident uh, 30, right? It is 0, and right here I put this is the incident ray, so it is 30 degree. I put it on 30 degree. If I put on 30 degree right here, how much is this? This is say nearly 20, right? It looks like little less than the 20, but this is 20. See, this is 10, this is 20, and 30, right? And right here is 30 degrees. So you can measure it by, yeah, you are measuring. uh, we are measuring. So uh, this is 30, this is theta 1, right? N1 we know, this is air, that's why this is 1. Let me do it right here so that it will be clear. Snell's law is N1. N1 means refractive index of this medium, first medium, then sine of theta 1. Sine of theta 1 means sine of angle of incident, this angle, which is 30, right? And then equal to N2. What is N2? N2 is angle of refraction, right here, theta 2. No, N2 is the index of this medium, right? And then sine theta 2. Theta 2 is angle of refraction, right? Theta 2. Okay, so we have everything other than N2. Suppose right now we have this one. That's why I'm just saying in this part you just have to check it. We know it should come 1.5 or very closer to this one. Okay. Uh, uh, what is this? This is 1. Okay. I can put 1 here, sine 30. So sine 30, right? This one is 30 here, is equal to N2, and then sine 20, right? Sine 20. Okay, look at here. What are the values of sine 30 and sine 20? So let me do on my calculator. If I put 30 and the sine, it means 0.5. 0.5 multiplied by 1 gives you 0.5. I'm just directly writing this one. You can do the calculation, right? This is the refractive index I need to know, which is N2, and sine 20. Let me put 20 and the sine, right? 0.34, 0.34, right? So what is N2? N2 is 0.5 divided by 0.34. Let me calculate this one. 0.5 divided by 0.34 gives you 1.47, right? It is very closer, 1.47. Look at here. It is very closer to this one. So I can see the error right here. There might be many errors. Never say in general like a human error. It's a bad thing, you know. What is the human error? You might be very careless. So that is not a like a real experimental thing. So you can say what it is, the particular thing. For example, in this case, why I am not getting 1.5 is I think I use angle of refraction, right? This angle is 30. It is more exact than this one. Look at here. This black line is out of this line. I think it's somewhere 19. Let me check with 19. I mean, this theta 2, let's 19. How much will come? Let's see. Just to show you how it makes the difference. Okay, so with angle 19 it will give you 0.32. if I put instead of this 34, if I put like 32, then how much is coming? Okay, 0.5 divided by 0.32. Awesome. It is 1.56. 1.56. Right? Um, is it closer? No, it's not exactly 19, not exactly 20. That's why it's somewhere between, right? But that's okay. 1.47 and 1.56 is very closer. I cannot exactly see these small lines are not visible. That's okay. If you get something like between 1.56 to 1.45, that is the good value, right? Your error will be something less than 10% or less than 5%, I think. Okay, or 0 point something. It could be very small, of course. So let me clear this one and go back to other stuff. Okay, so you can observe other things also. For example, if you wanted to check the intensity, what will happen when light passes from uh, rarer medium to the denser medium, you can check that. For example, right here, you can check the intensity, it is 100%, right? If you go here, see the intensity is also decreasing, right? And if you go here, this is the reflected light, intensity is very, very low, right? Also, you can check like, what happen if you increase the angle of refraction incident. If you increase the angle of refraction incident, angle of refraction is also increasing, right? If you decrease the angle of refraction, this is also decreasing. Okay, what is our next job? We go down, 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 and put mystery material A. Okay, let's do that. If you click right here is the mystery material. Okay, so with this mystery material, as like before, I don't know the value of n. That is, I don't know the refractive index. It looks like more denser right now. Look at here. If I put glass, it's rarer, right? Not dense. If I put water, it's more rarer. Water is more rarer than glass, and this mystery material A that we don't know what it is and how much is the refractive index of that material, we don't know. That's what we need to find it out through this experiment. Okay, so if I go down to this table and do the same process as I did before, then uh, look at here, angle of instant, you have to do same thing as before. Angle of instant, that is theta 1. Angle of refraction, that is theta 2, right? And calculate index of refraction of mystery material A. Formula is what? Snell's law. N1 sine theta 1 equal to N2 sine theta 2, right? So you can take the different measurement. When taking different measurement, you need to take 5 measurements, right? When you take these measurements, you can change the angle and just calculate, put into the formula and get calculated index of refraction. Okay, it will come same for any angle, because if you increase the angle of incident, the angle of refraction is increasing in same proportion, right? Let us do so that it will be clear. Okay, so for example, I want to start at 30 degree, 30 degree, right? Okay, so if you put this 30 degree, first of all, uh, you can write down the formula like this format. I want to calculate n. N1 I know, right? N2 I can say n. So you know the Snell's law, right? And this is air, so 1 into sine theta 1, sine theta 1. So 1 into sine theta 1, you can ignore this one. And for n2, you just can say n, right? Then sine theta 2. So I can write down like n equal to sine of theta 1 divided by sine of theta 2, right? Sine of theta 2, right? So right here, my theta 1 is 30 degree. So sine 30 degree is 0.5 as I get before. I don't have to put in calculator, I know that. So this is 10. This line is 10. How much is this angle here? This is 20. This is 15. This looks like something like 12. Okay, I can see that much. That's why I will put 12. So 12 sine. Okay, so I'm getting something like 0.21. Okay, so I'm getting 0.21. So this angle theta 1 I took 12 degree. Okay, for this theta 2 this is 12, and for this theta 1 I took 30. It's right here, it's straightforward, right? If I do calculations like 0.5 divided by 0.21, I'm getting something uh, 2.38. Okay, 2.38. If I, it's 8, okay, 8. If I round it off, it's about 2.4, right? This is the one data. Okay, so measurement 1, you can say this is measurement 1. Okay, so for measurement second, just remember, okay, I will erase everything. And for measurement 1 I get 2.4. So I'm erasing this data and increasing this angle, and I wanted to make like something. You can do any angle, but I'm just showing you two angles so that uh, you will be clear. Okay, I'm making exactly 60, right? So my theta 1 right now, my theta 1 right now, I'm directly putting into calculator. Okay, so theta 1, which is this angle, angle of incident, this is theta 1, and again this is theta 2, right? So always measure angle with this normal. Okay, incident, refracted, this is the normal. Don't take this angle, that is totally wrong. Okay, so sine 60, 60, and then sine. I'm getting 0.86. Let me put 0.86, right? Divided by this one is it looks like 20, 20.5. It's a little bit little ahead from 20, so I can say 20.5. So if I put like 20.5 and the sign, I'm getting 0.35. 0.35. Let me do the calculation and get another refractive index. So 0.86 divided by 0.35, and I'm getting 2.45, right? This is from second calculation, right? So remember from first calculation, I get value of n, which is 2.38, right? Okay, you have to do four calculations. I'm just showing you two. Okay, you can just change the value of theta 1, and then theta 2 will automatically changed. Okay, suppose that you can take like 20 degree or 30 degree, then 40 degree and 50 degree, whatever you like. Okay, uh, if I take the average, there is in your analysis part, you have to find the average. Let me find the average of these two. If I add 2.45 with 2.38 and divided by 2, and it is 2.41. 2.41. If I round it off, it is 2.4. What is this material? Unknown material. Could you guess it? You can Google it or see some physics books, I mean optics books. This is the diamond, right? 2.4, which is the very large value of refractive index. That's why diamond is sparkles, right? Everyone need diamond. Okay, so this is very exact value. If you are little off, that's okay. This is very accurate, because this is the simulation lab, and most if you are not doing something wrong, mathematics or somewhere else, then you should get this kinds of value. Okay. Anyway, I hope you understand how to do this lab and get the concepts about what the refractive index is. Okay. Uh, Let me see if there are anything that I can explain before I end this lab. Yeah, analysis first, there are a few questions you can do it. Here is the average. That's what you need to get average from 4 calculations and write it down right here. And you can also answer remaining questions. That's it.